My name's Kelly, and I'm a software engineer on the analytics engineering team at Etsy. And today I want to talk to you a little bit about the Julia language. I know we're at PyData, but PyData has had a Julia-related talk for a few times. Julia is a NumFOCUS sponsored project since 2012, and we are very good friends and siblings with Python. And so today I will talk to you a little bit about what's great and special about Julia and how easy it is to pick up Julia from a Python background. Python was actually my first programming language, and then I picked up Julia in college because I went to MIT. Julia was developed at MIT, and we used Julia to teach our linear algebra class. And I really liked how simple and fast Julia was, so I also joined the Julia lab at MIT and did my senior thesis there. And since then, I've been involved in the Julia community in a few different ways, and I continue to appreciate Julia and the people who make our community so special. And thank you for coming to my talk and for your interest in Julia. Let's dive right in. And so a brief agenda for today is an introduction to Julia, what I love about it, and how you can start coding in Julia today. This is a quote from the internet famous Worry Dream about Julia that I really like. Note that it was written in 2015, so I agree with everything said in this quote, but I also want to point out that since then, Julia has become a lot more stable and mature, and it has definitely branched out from just the scientific work branch. It's a very general language. People use it for pretty much everything. And especially with our much anticipated 1.0 release last year, the language has really evolved a lot. So first of all, why Julia? As we can see here, this is a periodic table of programming languages color-coded by their features. We already have a sea of languages offering different features. So why did the Julia creators and also the open source community think that it would be worthwhile to create a new language, given all those existing languages? And the reason why is because we have a two-language problem, in which traditionally a language is either performant, like Fortran, C, and the assembly language, or productive, like Python, Ruby, MATLAB. And so it seems like there is a trade-off between performance and productivity, and sometimes people have to translate between low and high-level languages. However, this is also not the entire story. We also need to consider generality, how regular rules of a language, without exceptions, are easy to learn, use, describe, and implement. And so if you need all those three features, a classical workaround is to use two languages. People will start with a language that they can prototype in, such as Python and MATLAB. And when they want to launch things in scale and need performance, they use a lower level language, such as C. And that gives us the two language problems. So when the Julia project started in 2009, its goal was to combine performance, productivity, and generality. And that was very exciting. And so a tagline for Julia that we like to say is, Julia looks like Python, feels like Lisp, and runs like C. And I will go through the three parts. First, performance. Here I have a chart comparing the run times for a few commonly used functions like loops and recursions in different languages compared to C. And we can see that Julia's performance is very comparable to C, and that's why we say it runs like C. And Julia code can actually be faster than typical optimized C or Fortran code sometimes, because it uses techniques such as metaprogramming and code generation that are hard in a low-level language. And Julia's multiple dispatch is a natural fit for defining number and array-like data types. And we'll talk about that in a little bit. And second, productivity. For a sum function, both Julia and C takes about 10 milliseconds, and Python takes about 500 milliseconds. But you can see here that the implementation between Python and Julia are not that different. So you're actually using very similar syntax, but getting more than a magnitude of performance improvement. And actually, I personally know a number of grad students who started using Julia for the first time because they had working Python code, but they wanted more performance. So they translated the Python code to Julia and discovered how easy that was and started using Julia. And finally, I want to talk about generality, and this is what we meant when we say Julia feels like Lisp, because Lisp has a large language center, including many built-in data types, functions, and macros. As we mentioned before, Julia uses meta programming, such as multiple dispatch. For example, I can write a bunch of collide functions like this, and when I run what I call collide xy, at runtime, Julia will dispatch the correct implementation, because in Julia, the virtual table is essentially stored on each function instead of on each class. When you call a function in Julia, it will look up in a table at runtime which concrete function it should be based on. It should call based on the type of the arguments. And in fact, multiple dispatch was a central design concept in Julia. Julia's standard library uses more than double the amount of overloading than in other languages, and more than 10 times in the case of binary operators. And another really cool thing about Julia is much of Julia code is written entirely in Julia, as we can see in this JuliaLand repo. And this is really cool because it allows users of Julia to also contribute to the development of the language. And actually, a lot of people start contributing to Julia because they were using Julia in their work or research, and they wanted to make some modifications to make things work better for their purposes. And now I want to talk about one application of Julia, the Celeste project. And it remains number one on the Berkeley National Lab's top 10 big data problem. So it all started in 1998. In 1998, the Apache Point Observatory in New Mexico began imaging every visible object from over 35% of the sky, and the project was known as the Sloan Digital Sky Survey. It included around 500 million stars and galaxies. Light from the most distant of those galaxies has been traveling for billions of years. But for 16 years, the process of cataloging the stars and galaxies was painstaking, and people didn't really want to touch the data set because it was so big, and this is how big the data set was. But in 2014, a team of astronauts, physicists, computer engineers, and statisticians from the Berkeley National Lab, UC Berkeley, MIT, National Energy Research Scientific Computing Center, and Intel began working on the Celeste project. They spent 3 years developing and testing a new parallel computing method that was used to process this huge data set. And this project was written entirely in Julia. It was able to produce the most accurate catalog of 188 million astronomical objects in just 14.6 minutes. It achieved a peak performance of 1.54 petaflops using 1.3 million night landing nodes on the Cori supercomputer at the NERSC, making Julia part of the petaflop club. And this last project showed us how Julia facilitated cross-department collaboration because the scientists, physicists, engineers, they all began working on the same code base from day one, and there was no translation from between high and low-level languages. And of course, the project showed us the superb parallel computing capabilities of Julia, which I also appreciate very much in the limited amount of research and work I've done using Julia. So now we have a general idea of Julia. I want to talk about what I really like about it. As mentioned in the beginning, I started using Julia in college, first in class and then in research. And then I've also used Julia at my work at Etsy a little bit. First, this is a slide from a numerical method class that I took in college. My project partner and I built a parallelized SVD algorithm. That is the singular value decomposition algorithm. It was for pure fun. We wanted to see if we could beat Julia's built-in SVD algorithm, which already was very optimized. And we wanted to see if written in Julia, we could beat Julia. And we ran our algorithm on Google Flume Java, which is a data parallel pipeline entrobed with C. And here I screenshotted a slide in our presentation. We came up with a pretty insane runtime. And also, we used Comic Sans for our presentation. But reflecting on that project, I want to point out a few things about Julia. First, Julia takes math very seriously. It excels at numerical computing, and the syntax is great for math. Julia also supports numerical data types, and together with the performance advantage, it was like a match made in heaven. I remember the days when I used MATLAB or Mathematica, and even for class projects, my laptop would like make really loud noises. And second, Julia provides parallelism right out of the box. Like even for something like that, we did a bunch of optimization parallelism. You can write parallel steps for even very small functions. Julia has several built-in primitives for parallel computing at every level: vectorization, multi-threading, distributed computing. Julia's native multi-threading allows us to take advantage of the power of a multi-core laptop, and its remote call and remote fetch primitive allow distribution work across many processes in a cluster. Oh, that is built for parallelism. And Julia uses a just-in-time compiler, which means code is compiled during execution instead of prior to execution, and this has benefits both in terms of performance and security, and it allows us to run more complicated models. And also, Julia can be easily integrated with Fortran, C, Python, and others. For that project, we integrated with C. There's a built-in class ccall where you can call C function directly in Julia. I personally also use pycall.jl package a lot, and there's also this really popular package in R called R-Julia. And in addition, Julia can be embedded in other programs through its embedding API. And then when I worked in the Julia lab, I actually did computational physiology research. And I really appreciate that we have Jupyter Notebook support. And I like to think that Jupyter is Julia plus Python. And there are also a lot of good plotting and visualization packages. And I like that there are a lot of options to choose from. For example, those are some plots that I made with the Gadfly.jl package. And Julia has a great package ecosystem. I think we're over 2,000 packages at this point, and a very friendly, supporting developer community. Personally, I'm a fan of BioJulia GitHub org. It contains a list of packages ideal for bioinformatics and computational biology research. And of course, again, Julia has great call support to other languages as well. And actually, in the project that I'm going to talk about next, I used RJulia a lot. And Julia has been increasingly popular among data scientists because of the many advantages we just talked about in terms of numerical scientific computing, performance, and productivity. At Etsy, I worked on a project to implement sequential testing on our A/B testing platform to limit peaking behavior from our stakeholders who were so eager to conclude their experiments as soon as they saw positive results. Because again, Etsy is an e-commerce company, and for a lot of new feature development, we run A/B test, and then we make product decision based on the result of those experiments. And I work on the A/B testing platform, and we and for a long time, we used p-value and power to indicate statistical significance, and so our stakeholders would just look at the result page every single day, and once they see that the p has reached a certain level, they're like, "Oh, yay, we can conclude the experiment." But we all know that's not the case, and that's the classic peaking problem. Um, so so we ended up implementing something like this like p-value threshold curve. But while we did the work, we did a lot of simulation and research into different methods, simulation of fake experiment data. And talking about data science, I'd like to talk about the New York Federal Reserve Bank. They've been using Julia for almost 5 years. They replaced a lot of their old models in MATLAB with Julia. And they use Julia to estimate models, which is 10 times faster than their old MATLAB models, to compare self-test, which is 11 times faster, and to reduce number of lines in half, which of course saved time, reduced error, and increased readability. And Julia has been increasingly popular, especially in fintech and insurance company. And for the New York Federal Reserve Bank, and actually me as well, we found that Julia handles more kinds of models more easily. And I specifically want to mention Julia's type system. It's dynamic, but also has some advantages of static typing. For example, you could indicate that certain values of a specific type, and you expect return of a specific type. For example, you can specify types of variables like unsigned 32-bit integer. But you can also create general cases like writing a function that accepts integer without specifying the length or signing up the integer. And you can also do it without typing entirely if you need it. The default behavior in Julia when types are omitted is to allow values to be of any kind. So we can use many useful Julia functions without ever explicitly using types. When additional expressiveness is needed, it's also really easy to introduce explicit type annotations. Adding annotations allows us to take advantage of Julia's multiple dispatch, which I had just mentioned. And in no particular order, I want to mention some other things that I love about Julia. First, Julia allows you to write pretty much anything, even a web application, and you can deploy it on a web server. Julia packages also naturally work very well together. This is thanks to the language's function composition, which makes it easy to pass 2 or more functions as arguments. Julia has a dedicated function composition operator for achieving this. This seems trivial, but I love Julia's indexing system. It's one indexed, and Julia's slice indexing includes the last element. And Julia 1.1 introduced the debugger suite, which executes code in a local read-eval print loop and allows you to step through the results, inspect variables, and add breakpoints in code. And this is pretty big for a new language. And at last, I like that Julia allows us to assign emojis as variable names. And so with that, I want to show you some real code in Julia and to see how it's very easy to start coding in Julia. Oh, where's my mouse? Yeah, and it's a notebook written by Andreas, who's from MIT, and with edits from me and Jane Harriman. First, arrays. I want to talk a little bit about arrays and functions before we before we dive into like matrices, arrays, it's very simple syntax. It's just like pretty much any language. Here we define Fibonacci. Oh, and also you don't have to always have the same type in an array. For example, here you can have integer and string in the array. And as I mentioned, Julia has one index, so to get the two strings, you would call 5 to 6. And to add and delete an element from an array, it's also pretty standard. It's just a push and pop function call. And functions. There are actually 3 ways to define functions in Julia. First is the one that I had shown in my slide. You would use a function and end keywords. Like you can say function, say hi, and print a line. Function define a very simple math formula. So when I say hi Kelly, it prints out an F18 gives me 18 square. And you could also declare functions in a single line, just using an equal sign, like this, and then it's the same. And also you can declare anonymous functions, like this. So when you run that line, it didn't say function say hi 3, it say function. That was the 23rd anonymous function that I had. So that's the number 23. And like this. So those are the 3 ways to define functions. And now let's define a random. So Julia's, a lot of the matrices, linear algebra related syntax in Julia is very similar to MATLAB. Here we define random matrix, and we can define a vector of ones using the fill call. And we notice that this A matrix has a type of integer 64 2, but X has type array 64 1. So Julia defines aliases vector as array type 1 and matrix as array type 2. And array operations. So I want to talk about the broadcast and map operations. They are pretty similar to R and MATLAB. For example, map, the syntax is like this. You're just getting the square of 1, 2, 3, 4, 5. And the broadcast function. Here we are adding up C, and we are adding 1 to each row of in D, 2 to each row in the second, 2 to each element in second row, 3. So that's the broadcast function. And basic operations are the same as in other languages. For example, multiplication is a star. What's different is Julia's call into program known as open blast, so that way it's an optimized multi-threading operation. For example, when we do the C dot star D, which is an element-wise multiplication, it will be faster. Transposition, it's also the same syntax as MATLAB. And we can get the transpose with transpose. Transpose multiplication, we can omit the star and just do A transpose A. solving linear systems, this is solved by the backslash function, which is also pretty standard. But note that a backslash b will give us the least square solution if we have an overdetermined linear system. Like this, give us least square solution. And it will give us the minimum norm least square solution if we have a rank deficient least squares problem. Like this, it's rank deficient. And Julia also gives us the minimum norm solution when we have a short matrix. So like this. And even though a lot of the linear algebra available in Julia is by default, there's also a standard library, linear algebra, and it brings in a lot more relevant names and functions. And as with using any packages, we can incorporate those features into our session using linear algebra call. For example, this dot call, it just gives the dot product, and this cross call gives it the cross product. And finally, I want to give a spotlight to views function. Here you can see that in the first case, making B didn't allocate an array. I just made an object with a pointer. Okay, this is actually all I want to say. It's all in the notes, but so the array itself is the memory layout, and for Julia arrays, this is actually a C pointer to a contiguous one-dimensional slot of memory. The array type in Julia is the view to the actual array. A view is a type which points to an array and has a compatibility layer that changes how things like the indexing works. And I think there's a pretty similar concept in NumPy as well, and it's also called view. But this array is actually a 16-number long sequence in memory, and A is a view to that array, which makes it index like it was a two-dimensional. Therefore, the A123 it isn't a view to the same memory, and we can check this we can say B is A1313, set B11 to be 100, and that doesn't change A because this first element is still not 100. But instead, if we want a view, we can use the view function. So we can call B as view A1313. And that way, when we change the element at 1 in B, that also changes A. Yeah, and there are cases where you might want to use a view, but we're not gonna go into that. And with that, that's all I wanna show. Just a little bit flavor into Julia. Alright. Oh, sorry, this. Okay. So, finally, I want to mention again just how great the Julia community is. It's full of very smart and kind people, and everyone is very willing to help. Whether you're a beginner or experienced Julia user, we would love to have you. And I said we have a ton of packages. The package ecosystem is constantly improving. And I'm actually involved in organizing JuliaCon. It's the annual conference for Julia, and attendees come from a diverse academic and professional backgrounds and different Julia proficiency level. It's a lot of fun and learning from and interacting with our global community. This year, I was involved in the diversity and inclusion effort, and next year, I actually will be the inaugural social chair. So I think it'll be the most fun JuliaCon. And at last, a lot of wonderful people have written some wonderful resources about Julia. This Intro to Julia link on the Julia Land official website has a ton of really useful links and tutorials to get you started. And I also want to mention two resources that I like in particular. One is a deep introduction to Julia for data science and scientific computing. It's written by Chris Kakakis. He is one of the most prolific Julia contributors. And another one is Think Julia, How to Think Like a Computer Scientist. The name might be familiar to you because it's written by the authors of Think Python. And I also included the centralized resources place for Julia packages. We have 2,367 packages at this point. A link to all the research that uses Julia, and also a link to how you can start contributing to Julia. It's very easy, and I think start contributing to Julia is a great way to also get started in Julia. And yeah, thank you so much.